Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be talking about the 4 basic operations of arithmetic with an incredible new applet which I'm going to make available to you for free. And I'm going to show you how to get those operations of arithmetic using only magnitudes and explain how they were transferred to algebra. If I don't finish in this part, I'll continue in the next part. So let's begin. Now, the first thing we need to understand is that the arithmetic operations are done strictly with magnitudes in the elements, and that's how the Greeks discovered the arithmetic operations. So each magnitude is identified by a ratio whose antecedent part, that means the part that appears before the colon, is on the y-axis. So I'm going to be representing them like this, putting the antecedent on the y-axis and the consequent magnitude on the x-axis, okay, this x-axis. And all that is required really is requirement 2 of Euclid's Elements and proposition 12 of book 5 of the Elements. And now we know that since a line through any point not on a given line can be drawn parallel, the blue and red parallel lines, these are the red and blue parallel lines, okay, can be positioned anywhere to arrive at the same result. So what I'm going to show you now how to do is how to do the basic operations just with magnitudes. Now, of course, I've included numbers here, but they don't need to be there, and you'll see why in a moment. So let's say we want to find the difference in sum, okay? So in this case here, we've got the red line, which is 3/4, as you see up here is 3/4, and the blue line, which is 1/2, right? And so all we have to do to find the sum is to position, okay, to position these lines, the parallel lines, on that cyan point, like that, okay? There you go. And that gives us the sum of the two or the difference, okay? So depending, so this 5 refers to this big line here, which is the numerator, the numerator, and the blue line is the denominator. But the way we find and represent these values is using the orange lines, okay? So the sum is given by this solid orange line over the solid blue line. It looks like a blue line, but it's more like cyanish as well. Anyway, and so the difference, of course, is given by subtracting the smaller orange line from the bigger one, okay? So if we subtract this smaller one from this bigger one, we have 1, but we don't have to subtract it in geometry. All we do is we take away this line length from this length, and to get the sum, we just join these 2 lines, and we know that can be done because requirement 2 says a line can be extended to this line or diminished again to this line, okay? And of course, this line here can be reduced to 2, which gives us the difference. Now, I've got a little button here called Easy Geometry, which tells you how to do these things, so I'll just show you very quickly. No, I didn't want to do that. Let's get that out of the way. Okay, that's there. And let's move that away, like so. Move that away. Okay, so if we've got 3/4 like that, Easy Geometry tells you draw a line through holy green point on red line. So this holy green point on red line and the y-axis that is parallel to the solid blue line. It's the same thing as just basically putting that green point over the blue point. Okay, so you don't have to do that because that's actually done in step 2. Okay, so step 1, you don't really do anything. Step 1 draws this holy, not this holy, this dotted line, this dotted blue line through this holy green point on the y-axis. This is what step 1 does. Now step 2 says you move the solid parallel red line, the solid parallel red line, it doesn't really matter which order you do it, on the green point so that it overlaps like that. And then you move the solid blue line of the green point so that it overlaps like that. And then, of course, once you do that, you can get the sum and difference, or you can even look at the quotient. Okay, so the quotient is given by what? It's given by 4.5, which is this line here, in ratio. It's the measure of the ratio of this long line to this short line, right? So strictly speaking, we could have just said, let me get a drawing object, a pen. So we could just say it's the ratio of 4.5 to 3. Okay, so that's the ratio. Now the measure of this ratio in magnitudes turns out to be 4.5 over 3, which is 3/2. Okay, so it turns out to be, the measure of this ratio turns out to be 3 over 2. Now, I don't want to deal with that anymore, so let me just get rid of this. Okay, let's just delete that. Now, the product is actually the reverse of a quotient. It's defined in terms of a quotient. Now, remember, in well-defined concepts, the most primitive operator is the difference or subtraction. Then we have addition or sum, and then we have the quotient, which is the one I just showed you before. It's this one here, the quotient. And then finally, the product or multiplication. So now how do we find the multiplication? Well, what we have to do is we have to invert this blue line, because the measure in multiplication happens when we switch the antecedent with a consequent of one of the ratios. So what we do here is, this is the original 3/4 that we had when we looked at this, right? Original 3/4. But now we switch that, so we've got this magenta dotted line, and this is the one we need to measure. And so again, we do the same story, just bring that line down there and that line down there, and there we've measured it. So the product of this is 3/6, or not 3/6, 3/8, or 0.375 in decimal. Okay, and so 3/8 is the product of these numbers, and it doesn't matter which way you do it. You can reverse. For example, you don't have to do the 3/4 one. You could say, okay, let's switch these around and let's do this. Let's make the 3/4 a half, like that. Oh, no, not that one. Sorry. 3/4 a half. Get that out of the way. It's that line that I want. So I want a half there, a half like that. Okay, and then I want to make that 3/4. 3/4 like that. Come on. Yep. Oops, did I get that right? No, that's not exactly on 2, and this is not exactly. Now it's exactly on 3, but this here isn't on 4. Now it is. Okay, so now, and again, we do the same story. We just put the red line on the sign dot as well as this line like that, and the result is the same. So in multiplication, which is the reverse of division, we say we take this operand and we flip the second one. So this is the second one flipped, as you see in magenta here, okay? And of course, the measure turns out right. It's just this line in ratio. It's the measure of this line in ratio to the measure of this line. Okay, so now, what's the conclusion of this whole thing? Well, let's see. So the conclusion says that all the arithmetic properties are transferred to algebra through the abstract unit in Book 7 of Euclid's Elements. So what does it mean through the abstract unit? I've talked about that a lot. So let's quickly go over it. I'll explain it. In geometry, we identify magnitudes through the use of ratios. So that is, if P is some line segment, then we can only differentiate it from other line segments when it is compared to a given line segment. So another line segment, Q. So the ratio, that is PQ, P colon Q, where P is the antecedent magnitude and Q the consequent magnitude. So for example, ratios can be in proportion without being equal, like these ones that you see in figure 1 here. So you see all these ratios are in proportion because the measure of all of them is a half, but they're not equal because the important part here is the antecedent, which are these solid red lines before the colon. Okay, we use the consequent to measure the antecedent. And so this is not the case with respect to the measure of a ratio, which is a number. Okay, the measure is the same no matter how the unit or the consequent is chosen. Doesn't matter how you choose it. So in algebra, unlike geometry, the abstract unit is partitioned, well actually like geometry, the abstract unit is partitioned into equal parts for the process of measuring the antecedent. So we can measure the antecedent with one of these equal parts, and again here this antecedent with one of these equal parts, and so on, right? So the concept of a ratio of magnitudes is extended to numbers so that the numerator and denominator are the algebraic analogues of antecedent and consequent respectively. So in this video I've shown you all the operations using only magnitudes, and I've given you a very powerful applet which uses similar triangles. As you see over here, the reason this trick here works is because I'm using similar triangles, see? Okay, so when you do easy geometry and you do step 1, all I'm doing is I'm creating a magnitude that is common to both, an antecedent magnitude, which are the ones that you see down here, okay, an antecedent magnitude that is common to both of these. And it's very easy to do because I'm using parallel lines, right, as you see over here. And all I do is I just position them at the same spot, so now they have the same magnitude, and now I can actually take the ratio or the measure of the ratio, which is given by the orange lines. Well, that's pretty much it. This is one of my best applets so far, and I hope that you will download it. It's available if you just send me a request for Google. It's not, I have no control over that. Google wants you to, because of security purpose, wants you to request it. And then I have many brilliant articles and videos on this site here, which is called academia.edu. And I suggest you go and visit that site, and you can download these without requesting them from me because they're free. I think you might have to sign up. I'm not sure of that. But anyway, it's all written here. So I have over 64 articles and 65 papers, in fact. Yeah, 65 papers, 1 book, and 5 videos. So that's pretty much it. If you're not already a subscriber, become a subscriber. I'm thinking of posting this video also on YouTube because it's such an important video. And then, of course, follow me on Odysee because that's my main channel now. I'm no longer uploading videos to YouTube. Except in this case, again, I'll make an exception because it's such an important topic. You know, a number is a name given to the measure of a magnitude. And that's something that most ignorant mainstream academics in mathematics do not understand. Spread the news of my channel and become a subscriber and click like. And hopefully, if I'm well enough, I'll be producing more videos and uploading them to the Odysee site. I'm John Gabriel. This is a new calculus channel. Till next time, goodbye.